Hey there, Math 126 students. I just wanted to say a few things about double integral applications. In this course, because of time, we pretty much just talk about height. We have a few questions about density, but I just want to talk about applications briefly. You have learned to describe regions. You now know how to describe this in terms of x, how to describe it in terms of y, and how to describe it in terms of polar. And you could pick whichever one you like. And I think of double integrals as measuring something that's happening over a region. It basically does, what it does is it breaks it up into all these little pieces, adds things up, and then we can do stuff with it. But we saw one application was that if you do the double integral over that region of f of x, y, let's pretend that this represents the height in maybe feet or something, then that's going to give you the volume. Now, in terms of units, that makes sense because if this is in feet, the area of the base is going to be feet squared. And so this is cubic feet. But what we're really doing, as we talked about when we did the Riemann sum idea, was that we were multiplying times the height, which was the f of x, y, times the area of the base. But we do multiplication like this in many situations where it doesn't represent height, but it represents something else. So this still would do the same thing. In this case, it was adding up the height times the area of the base, but what other things could we have there? And we did see one other small application, which is if you put a 1 there, this is a more geometric application, this ends up just being the area of R, which is kind of interesting, but let's move past that. So what if it's just some other random thing? So what about temperature? Let's pretend this is like a hot part of a beach or something, and you have the temperature at each point. And maybe it's getting hotter or colder, or maybe it kind of fluctuates as you go across. Let's say it's degrees Celsius. That's going to be really hot if I do that. Let's say it's 90 plus x squared plus y squared. So it gets hotter as you go out. And we would like to add up all the temperatures. So if you add up all the temperatures, you get this, the double integral over r of 90 plus x squared plus y squared dA. And you would say, well, I probably want to do that in polar. So it doesn't change how you set it up. If I did it in polar, I would say 0 to pi over 2. I would say 0 to 2. I would say 90 plus r squared, r or d theta. But what that's going to give you is degrees Celsius, which is what this is, times the area of the base, times square meters, which doesn't really make any sense as a unit. But what we then do is we divide by the area. And it turns out if you divide by the area, you just get degrees Celsius, and that represents the average temperature over the region. So I always like that as an example because it shows you something that's not a 3D object at all, but it is measuring some function. So if you do the double integral, divide by the area, it's actually the average value. In this case, it would be the average temperature. And I always use that as an example for the course that follows when we do triple integrals, because I could say, well, it makes sense to measure the average temperature like in your room. Okay, let's see some other things. So another one, I got rid of my axis. So we sort of talked about average temperature. You could have average other things. So the next thing we move on to is density, something where we know the density at each point. Meaning like if you cut out a little box, we know what the density is. There's charge density and then there's like mass density. So if you take a physics course, they might say, we know the charge per unit area. We want to know the total charge on the entire object. You say this. You just integrate. And that's what that does. So if you have some sort of density, it's basically doing density times square meters. This is going to be in columns or just density. Now the one we do in our class is what if this is the density in terms of mass? So this is kilograms per square meter. and this is meters, we call this the total mass of the system in kilograms. So that's a nice little example. And then putting it all together, in physics there are these things called first moments and second moments that measure how the mass is distributed, how likely the thing is to rotate, all this stuff. And the first moments are these: y, f of x, y. This is actually called a moment about the x-axis. Yeah, it's a physics terminology thing, so blame them. And then you have this, which is called the moment about the y-axis. And it turns out that if you do this weighted average, watch my previous video on that, you get x bar ends up being this one with the x's in it, divided by the total density of the system, total mass, sorry. And then you do the same thing for y bar, and that's our formula. Turns out there is something called a second moment where it's basically exactly the same, but there's a y squared. That gives you more information about how it rotates around a point. But again, that's for your physics class. Okay, so I just wanted to sort of recount a few applications that you might see in the future. But the thing I wanted you to see here was we can describe this region now. We've learned that skill. So in the end, this just gives you a broader picture of what we've done is we've learned to describe regions, which helps us for computing any of these things. All right, hope that's interesting.